Welcome back, everybody. So let's start the second session of the second day by Jee-Woo Park. He was going to talk about the second lecture on
Yep. All right.
Over to you.
Thank you. Thanks for the introduction. By the way, people who really know me call me Peter. So if you ever have to speak with me, you just grab me and call me Peter. So this will be the second installment of the 3 lectures that I prepared on long-range interactions in quantum gases and tweezer arrays. Yesterday, I kind of did an overview of how cold atom experiments work, how we prepare them using laser cooling, and within the atomic gas experiments, how long-range interactions are used using a probe using magnetic atoms. So that was here. And today, so yesterday after I finished my lecture, there was some questions or requests asking me to go over the very end of yesterday's lecture in a little bit more detail. So I'll do that with the physics of supersolidity. And then starting from today, I'll take you guys on a tour of my neighborhood, which is the experiments with polar molecules. So today I'll mostly focus on talking about how we make polar molecules in our experiments. So it might be a little bit more boring for the theorists out there, but then on Thursday, I'll start to talk a little bit more about how we induce long-range interactions in polar molecules and how the way in which we induce them is quite different from how the experiments with magnetic atoms and Rydberg atoms work. Okay, so that might be a little bit more interesting. So going back to the very final slides of yesterday's lecture, so I'll pick up on this notion of supersolidity. And this physics of supersolidity, at least in a pictorial sense, you can approach it from, oh, you're stretching. Yeah. Okay. You can think from 2 directions. You can start off with having a superfluid, which is a fluid that you have that can flow without friction. And then going from a superfluid to the supersolid phase would be having periodic modulations that look like a lattice that in some way spontaneously form in your many-body system. The other way would be to start from a solid, which is an irregular array of or ions or some structure. And then from there to going to a supersolid phase would mean that you have some level of phase coherence within these different periodic structures. So you have phase coherence over the global many-body system, so which becomes a supersolid. And this notion of the existence of the supersolid phase, as I said, has been discussed since the early 1970s. And the seminal experiment that was actually probing, I think I'm not so sure if it's the very first time, but at least the experiment that gets referenced is this experiment by the Chan group at Penn State University with helium in their very cold helium, which presumably becomes a solid, and they do this torsion oscillation and try to measure the moment of inertia in these experiments and try to figure out if that, from that signature, they can figure out whether if the solid has become a supersolid in the sense that it doesn't have friction. But this result has been, I think, well, I don't really follow the helium community in a very tight way, but to the best of my knowledge, this experiment has been refuted in 2012 by the same group, the Chan group at Penn State, saying that the same experiment was observing not supersolidity, but a different feature of solid helium in their torsion experiment. Within the atomic gas community, especially the people who work on magnetic bosonic atoms picked up on this theme and started probing this physics of supersolidity. And to understand that, a good starting point to discuss is the Hamiltonian of interacting bosons. And I think in yesterday's problem session, you already got one very big piece of equation that's essential for understanding the physics of superfluidity, which is the Grosseteste equation. I would say that the second equation that you need to know in order to understand and study interacting bosonic gases at low temperature is the Bogoliubov equation, or the Bogoliubov dispersion, or the derivation of the dispersion. So, I rushed through this slide, so I'll take a little bit more time this time around. So imagine that you have a gas of interacting bosons in your space. Let's say they're uniform. And you try to write down the Hamiltonian of the interacting bosons while including just pairwise interaction. So you would normally write down your kinetic energy term and whatnot in real space, and then you take a Fourier transform because you have a uniform system with periodic boundary conditions, which gives you the Hamiltonian in momentum space in second quantization, which would look like this. So you have your kinetic energy term, your free particle dispersion, diagonal in the creation and annihilation operators of the bosons. And then you have your pairwise interaction where you annihilate k prime bosons, and then you create k plus q and k prime minus q pairs through the interaction. So to go from this generic Hamiltonian of two-body interacting bosons to the physics of a Bose-Einstein condensate, the simplest way to proceed is to take the mean field approximation. So you assume at very low temperatures the majority of your bosons are condensed in the ground k state, k equals 0 state of your system. So you approximate your A0 with the square root of the number of the atoms that you have in the ground state, in the condensate. Similar for the A dagger, a 0 term. And then you try to simplify the two-body interaction term with the assumption that the majority of the atoms are condensed in the ground state. So you plug in this mean field approximation into your two-body Hamiltonian. Then from the kinetic energy term, you would have the summation over the excited kinetic energy states over their occupation. So this sum, normally you just write it as k prime, but it's okay to include the 0 because E sub 0 of 0 is 0. So that's fine. And then now taking a look at the interaction term, you only want to keep orders up to two creation and annihilation operators. So you can only keep the terms, you can decide to keep the terms that have two of the four A operators with indices equal to 0. Right? So one term, one possibility would be that all of these indices are 0. For k, k prime, and q are all 0, which would give you the BEC self-interaction energy. So this is just a pair of atoms in the bosons that get annihilated, interact, and then become created in the condensate itself again. So that's just the self-energy of the bosons. And then the other terms you could have, for instance, is a case where k prime and k is equal to 0. In which case you would have the A dagger q and the A dagger minus q term. So in a physical sense, what that means is that you have a pair of atoms in the condensate because the AK prime and the AK, K prime and the K indices we're taking for 0 right now. So a pair of atoms in the condensate interact and then become an excited pair in the non-condensed state. And you can play this game and then see that you end up with this Bogoliubov Hamiltonian, or this mean field Hamiltonian. In addition to having the BEC self-interaction energy term, you have this term that accounts for the interaction between one atom in a condensate and one atom in an excited K state. And these two terms that account for the interaction between a pair of atoms in the condensate after colliding becoming a pair of excited K state atoms, and the reverse of that. So two finite K atoms interacting and then becoming a condensate pair. So that's the kind of the working Hamiltonian that we will use to treat the condensate at the mean field level. And of course, to diagonalize this, we use this trick of Bogoliubov transformation. So you define your alpha and alpha dagger quasi-particle operators with the additional freedom of these amplitudes. So kind of, as I said yesterday, you have some level of gauge freedom that you can get rid of using this constraint. And you can plug this into the Hamiltonian and chuck the math and end up with a diagonalized Hamiltonian that looks something like this. So this is the self-energy term. This is the energy term that you get from, for the ground state energy shift that arises from the interaction of the atoms in the condensate and the atoms in the finite K state from the excited particles. And then you have the diagonal dispersion term, which is the Bogoliubov dispersion, with the energy given by the square root of the free particle dispersion squared plus the free particle dispersion times the density times the Fourier transform of your interaction, two-body interaction. Okay, so up to this point, is everything okay? Yeah, cool. So then, now moving on to understand dipolar Bose-Einstein condensates. The interaction that we have to work with is not just the contact interaction that we would normally work with for the case of just alkali, a pair of alkali atoms. But now, because you work with magnetic atoms, you have this dipole-dipole interaction term, which is proportional to 1 minus 3 times cosine squared of the theta of the angle of the dipoles over r cubed. And following our procedure, we take the Fourier transform of this. The Fourier transform of the delta will be just a constant g. And the Fourier transform you can work out for the dipole-dipole interaction. It will come out to be this term. And you plug this into the dispersion, and you see that for the case of 3D interacting dipolar atoms, magnetic atoms, the dipole-dipole interaction term doesn't really have any sharp K dependence. It has a very strong angle dependence, right? So in 3D, if your dipoles are aligned like this, they're repelling. If they're colliding like this, they're attracting. So for imagining, you have a Bose-Einstein condensate, a weakly dipolar Bose-Einstein condensate, and you align your dipoles in plane with the superfluid, then the axis along the alignment of the dipoles, they're attractively interacting. So they'll become denser in that axis. Whereas in the perpendicular direction, they're repelling, so they'll bulge out. Okay. So 3D, that's kind of the physics that you expect to see with a weakly interacting dipolar gas. But of course, things change once you induce strong confinement in your system. So once you assume that now, instead of having your atoms in a 3D trap or in a uniform trap or whatnot, that you have these atoms confined, let's say, in a pancake trap, like this. Then to get the correct dispersion, then you need to integrate out this tight confining direction, right? So you would integrate this interaction term over the harmonic oscillator wave function of the z-axis in the momentum space. You take the Fourier transform and integrate over that. And when you work that out, you'll see that it actually gives you a very strong K dependence, which is set by the thickness of your sample. I didn't write out the equation itself. I think if there's enough interest, I'll try to go through this on the blackboard on Friday, if that will be helpful. So if you do this calculation in 2D, you'll see that at the characteristic K value, which is determined by the inverse of the thickness of your sample or the inverse of the thickness of your confining axis, you see a very strong attractive dip that forms in the dispersion for these dipolar bosons. So that's on the level of chugging math, but on the level of thinking about the physics behind it, as I said, the reason why such this dip in the dispersion, attractive dip in the dispersion occurs at this particular K is because if you think about the range of, if you think about the collision of a pair of dipolar atoms for small momenta, let's say, for small k, kind of you can think of this interaction, you can kind of visualize this interaction as having a very kind of long contact parameter, for instance. So this interaction in 2D will really look like a 2D interaction. So if you imagine that for the experiment that's confined in a single plane, if you align your dipoles perpendicular, so the experimental situation is that your dipoles are aligned perpendicular to the confining 2D trap. So then for these small k interactions, your interaction really looks like repulsion. Right? But for very high momentum, this contact parameter is actually much shorter than the characteristic distance along the tightly confining direction. So for these very high K collisions, your interaction actually has an attractive branch along the tight confining axis. So that's the reason why you see this kind of attractive lowering of your dispersion at this K value. And this dispersion, the particular shape of the dispersion, it's a very historic shape of a dispersion going back to the early days of helium studies, and it's called the Roton minimum.
Yeah. So there is the base of superfluid.
Yeah.
And dipoles are of what?
Perpendicular.
What are the dipoles? Like
Magnetic dipole.
Magnetic
Magnetic
dipole.
dipoles.
So when they are perpendicular to the superfluid, then they don't form condensate, or
They do form a condensate,
and
as long as the interaction is not too strong.
not too strong.
Yeah.
And when they are in plane,
In plane, they can still condense if the interaction is weak. Okay, so in a strict 2D, it wouldn't be a BEC, but it can be a superfluid. But if it's quasi 2D, yes, they will condense. But it'll be anisotropic.
what's the anisotropic?
If your dipole moment is in plane, the shape of the condensate will be not round.
Anisotropic.
Yeah, it'll be anisotropic. Yeah. But this part of the experiment, I'm assuming that the dipoles are aligned perpendicular. Yeah. Say again?
Global phase, supersolids have a global phase.
Yes.
Do you see that in this?
Well, I guess the assumption is that already the bosons have condensed when I decided to work with the Bogoliubov Hamiltonian. So it's already built into the Hamiltonian, I would say. Because I'm already assuming that the A0 has a finite occupation. And presumably I could, if I were to write down the wave function, like in the Krosby-Tayevsky formalism, I would have written it down as a square root of n times the phase factor. So I would already assume that there is phase coherence. So because of this Roton minimum, it turns out that as you increase the strength of the dipole-dipole interaction relative to the S-wave scattering interaction strength, which is parameterized by the S-wave scattering length A sub S, you see that this Roton minimum becomes stronger, which at some point even becomes negative. So this is the point when the dipolar condensate becomes unstable towards the formation of these periodic structures, which has a very finite, well-defined K value, so that will be periodic in your gas, with the wavelength corresponding to 2 pi over the Roton K. So typically, when you have a channel where Bose-Einstein condensate can become locally very dense, you have this physics of inelastic losses that occur in the bosonic gas. Usually your bosonic condensate dies, essentially because of the inelastic collision. For this particular experiment with magnetic atoms that I don't want to go into too much detail, there's another mechanism that competes with this collapse of the condensate at this finite K, which is this celebrated Li Huangyang beyond mean field term that kind of protects your atoms from becoming too dense. It gives you an effective beyond mean field repulsion if you treat it correctly. But I don't want to talk too much about that. So that's kind of the reason why in these systems you would imagine to see a periodic structure in your condensate, spatially periodic structure in your condensate, which could potentially correspond to the formation of a supersolid. Okay, so then experimentally, you go cool these bosonic atoms, confine them in 2D or in 1D, cool them to very cold temperatures, and then align them perpendicular to the confining axis and see whether if such a spatially periodic structure would form, and indeed they do. But still, the big question of the experimental question of whether if there's phase coherence, global phase coherence within your condensate you have to experimentally show. And that's the very non-trivial part of these experiments. So since the first experimental exploration of this physics in the late 2010, around 2019, a couple of different groups around the world have put this physics of supersolidity, or the global phase coherence, into test. So the Italian group decided to rotate their trap or kind of oscillate their magnetic field in a way that they can really emulate the classical torsion experiment that people with helium did in the past, and do very careful theory and try to match or calculate or match the theory and the experiment, or match the experiment. Well, okay, I should be careful with this. But you see what I mean to say. So you do a very careful theoretical calculation of what the torsion oscillation frequency should be, and see if that matches with the frequency that you would theoretically calculate for the supersolid phase in comparison to the typical normal condensate without the periodic structure. And it turns out the experiment matches quite well with the theory. And another group very recently tried to create vortices in the supersolid. So if you work with Bose-Einstein condensates, kind of the hallmark of having global phase coherence, the experimental smoking gun proof is to see quantized vortices in your gas. And if you have typical alkali Bose-Einstein condensate, vortices are very easy to detect. They really show up in your density distribution as a whole that pokes through your gas. But with this periodic structure of the supersolid, together with the vortex, I think it's a little bit more challenging to kind of discern the existence of vortices in these images. So these are the density distribution, presumably in the super solid phase, in the presence of a vortex. So it's not as visually obvious that you have a hole that's poking through your supersolid sample. But what they do is they also do a very careful theoretical calculation of the density and also of the phase of your global phase of your gas, local phase, and you really see that there are vortices that has a phase winding around. So that's kind of the experimental probe of testing really supersolidity in these dipolar Bose-Einstein condensates. So hopefully that was a better explanation than what I've done yesterday. And so the physics that I've shown you, the formation of a weakly dipolar condensate to supersolid phase to independent droplets is in the regime of weak to moderately interacting dipolar gases. But you can think about what will happen if you really push this limit to the extreme. So very, very strongly dipolar gases compared to the contact interaction, to the SO's short-range interaction. And what turns out is that you expect, on a theoretical level, for these dipolar crystals to form in 2D. So these are really crystals of individual atoms or molecules in your trap that organize by themselves through dipole-dipole interaction. So far, experiments with atoms are probing kind of this regime. By the way, the y-axis is just a normalized temperature. So for hot gases, you'll be in the normal phase, low temperature superfluid. And the question is, how can we go towards this direction and prove the phase diagram? And for that, I don't think, so one way to do that would be to enhance the density of your dipolar gas, which I've said it's not that trivial because you have losses at high densities. And another way is to increase the dipole moment of the particles that you work with. And the natural way for us to do that is to use polar molecules instead of dipolar atoms, which is one of the many motivations for us wanting to work with cold molecules. And so a recent theoretical paper also did a rather careful simulation. I think these are maybe GP simulations. As a function of the number of atoms in a molecular BEC versus the S-wave scattering length for different dipolar interaction strength, and see very exotic kind of modulated structures appear in these 2D gases. So it's a very interesting direction that people hope to probe in the future. And on an experimental level, with molecular Bose-Einstein condensates, so the first time molecular Bose-Einstein dipolar molecular Bose-Einstein condensates have been created is in the year of, well, at least the paper was put up on 2020, late 24 or 5, so very recent. And the same group at Columbia University, Sebastian Will's group, have started probing kind of similar physics that magnetic atom people have been probing these formation of droplets. So gradually we're working towards this regime of very strong interactions.
How those photos have been taken?
These are not
Not these. Left side.
these are just shadows of the density distribution. So you have your condensate, you shine in resonant light, atoms will absorb, leave a shadow behind. You image that with the camera. Yeah. Okay, so that gives me a very good entry point to, or a motivation of why I would want to talk about ultracopolar molecules. Okay, well, I've already used 30 minutes of my time. So just saying what I said yesterday again, atoms are great, but of course we want to study systems with long-range and anisotropic interactions. And yesterday we treated this. Today we'll talk about this. So one thing about polar molecules is that that I won't be able to talk about today, but I'll be able to talk about on Thursday's class, is that the interaction is actually induced. So you have the control over the size of the dipole moment. You have full control over the size and the direction. I'll get to that on Thursday. So that's a bit different from the control that you have over magnetic atoms using permanent magnetic dipoles of the electrons. Okay? So what's kind of the simplest molecule that you can think of that has a non-trivial electric dipole moment? It would be a diatomic molecule, naturally, or just one more atom than a single atom. And you better make these two atoms different. Otherwise, these molecules will not be dipolar. So if you have a homonuclear diatomic molecules, these are not dipolar molecules. So the way in which these molecules acquire an electric dipole moment is because the electronic cloud of the two atoms is asymmetric. So along this fixed axis of the molecule, you have like non-trivial electric dipole moment. Okay? And even for very simple diatomic molecules like these, the electric dipole moment can be as large as 10 dBi. As I said, the water molecule has about 1.85 dBi. Comparison to magnetic atoms that have about 0.01 dBi. That's a huge increase in the size of the dipole interaction. It's actually the square of this increase of the dipole moment itself. So they're very dipolar. And with these molecules, obviously there are a number of different routes that people can imagine using them for future application. Obviously one is using them to study exotic dipolar many-body systems, put them in a 1D optical lattice in a pancake, tilt them and see exotic pairing mechanisms, for instance, P-wave superfluids, supersolidity, crystallization, and so forth. But you can also put them in stacked layers of these traps and see interlayer interaction, long-range interaction. Second direction is in the direction of quantum computing. These have not as strong dipolar interaction as Rydberg atoms, but they still have sizable interaction. So if you put these molecules about a micron apart, which is kind of the typical spacing between tweezer arrays, the interaction strength in units of frequency would be on the order of kilohertz to 10 kilohertz, which is not too slow. So you could use the dipole-dipole interaction between a pair of molecules in, for instance, in tweezers to implement entangling gates. Typically in these molecular platforms, we choose to implement the I-swap operation instead of the CNOT gate. Maybe I'll talk about that a little bit more on Thursday. One Another aspect of using these molecules, cold molecules, for future applications is in the direction of quantum chemistry. So if you think about a molecule, the basic structure of molecules, I'll talk about it in a few more slides. Well, what's the smallest energy scale for an atom? If you're working with atoms, what's kind of the smallest internal energy scale that you have to work with? Be the hyperfine interaction, right? The same, it's the same for molecules. So molecules obviously are also going to have some rich level of hyperfine structure. And the typical energy spacing between the hyperfine levels in these molecules, if you compare that energy to the typical temperature of these very cold molecular gases, we're at least an order of magnitude colder. What that means is that we can prepare a gas or an ensemble of molecules all initialized to the same hyperfine state. So this is a very different situation from kind of a typical classical chemistry experiment starting point, right? There you have finite temperature. You have room temperature chemistry. You do have quantum mechanics deep in the ground, but all of the levels, they're just washed out by the Boltzmann distribution. And the reactions are all averaged, thermally averaged. Here, for the first time, we have the opportunity to probe chemical reaction at the single quantum state level. And if you become very imaginative, you could, obviously the rules of chemistry that deal with the quantum regime, the rules are going to be very different from the rules that deal with the classical regime. So you could imagine understanding quantum chemistry to the point that you are able to produce new types of molecules. And in the long run, maybe, that could lead to development of new materials and maybe new types of medicines in the far, far future. So that's kind of why people are very interested in creating these very cold molecular gases. So then the question arises of how we can actually go about creating these dipolar molecules. And I'll give you a fair warning and say that it's much more complicated than just cooling atoms to the nanokelvin temperature range. Okay, so the reason why it's so complicated is because molecules have much richer structure. Just by having one additional atom there, you not only have translation, center of mass translation of your molecules, which is also there for atoms, but what the atoms don't have is, for the molecule, you have the degree of freedom for them to vibrate, rotate. And on top of that, you have hyperfine interaction from all the various electron and nuclear spins. So the internal structure of the molecules is much more complicated than just the typical alkali atom. And that puts very tight requirements on, or kind of limits on what we can actually do with these molecules. So if you have an atom in the ground state, you shine in a laser and you excite them to the p manifold, what that would look like for the case of a diatomic molecule, you would have a molecule in the ground electronic potential in the ground rotational state. You shine in a laser beam and you excite these molecules to a vibrational state of an excited electronic potential. I'll explain a little bit more what this means for molecules. So the way in which we understand molecular structure, at least for people like me who are not theoretical quantum chemists, we rely on the Born-Oppenheimer approximation. Okay? And so we can visualize a diatomic molecule as having nuclei and outermost electrons. It's a few-body system of these particles. And because the distance between the nuclei is not too far, the electronic cloud actually overlap in between. So for bialkali molecules, I tend to think of this binding as a form of covalent bond. I'm not so sure if the chemists would agree with me, but I think they would, because they share, the two alkali atoms share the outermost electron and become more stable. So if you write down the Hamiltonian for a single molecule in this picture, then you would have the kinetic energy of the nuclei, you would have the kinetic energy of your electrons, and then you would have all the pairwise Coulomb attraction and repulsion between the nuclei and the electrons, which is just this term. And you would have the fine structure interaction and hyperfine interaction. Okay, so then if we want to understand the molecular structure, we would start from this molecular Hamiltonian and try to solve it, find the eigenstate and the eigenenergy of this given molecular Hamiltonian, which I've said already on yesterday's lecture. It's a very challenging quantum mechanical few body problem that people use quantum computers to deal with. So the key approximation that allows us to go further, one of the key approximations is the Born-Oppenheimer approximation. And the statement of the Born-Oppenheimer approximation is that electron is much lighter than a typical nucleus. So the motion of the electron is much faster than the nuclear motion. So for a given coordinate of the nuclei, the electrons will instantaneously adjust to that position of the nuclei. So from the perspective of the electrons in the molecule, what this means is that we can treat the nuclear coordinates as kind of parameters and try to deal with the electronic problem first. So relying on the Born-Oppenheimer approximation, we can write down the molecular wave function as a product of the electronic wave function that depends on the coordinate of the electrons, lowercase r, but takes as an input, as a parameter input, the coordinates of the nuclei, as capital R, times the wave function of the nucleus. You put this into the molecular Hamiltonian to the electronic Hamiltonian. So you only keep the kinetic energy term for the electrons. And then you have the potential. And once you write down your molecular wave function as a product, the agenda to do is then to solve this eigenproblem and try to figure out the eigenenergy for the electronic wave function first. So for a given r, the potential only takes as the coordinates of the electrons as variables, right? The large r is just some constant. So presumably, the Coulomb interaction of the electrons with the nucleus, the positions of the nucleus is fixed. So you can numerically solve the Schrödinger equation as a function of the position of the electrons and figure out the energy, electron energy, E sub L. Okay? And then what you do is you plug that into the full molecular Hamiltonian. So the full molecular Hamiltonian times the full wave function is just going to be the previous term, the electron Hamiltonian plus the nuclear kinetic energy term. And then you have your product state. And because you've solved the electronic problem first and figured out the electronic energy potential, E sub EL, now the problem simplifies so that you have an effective potential that's generated by the electrons for the nuclei, plus the nuclei kinetic energy. Okay? And because the electron wave function is just the eigen function for these two terms, the Schrödinger equation simplifies such that you have an effective Schrödinger equation for the nuclear motion. So you have the kinetic energy of the nucleus, the electronic potential that's generated for the nucleus, times the nuclei wave function, and you solve for the eigenenergy of this. And this potential that the electrons generate for the nuclei is called the Born-Oppenheimer potential. And the potentials that I've drawn here are the so-called Born-Oppenheimer potentials. So these are the potentials that the electrons made in a way that the nuclei feel and vibrate. So for a diatomic molecule, solving the nuclear Schrödinger equation amounts to having the kinetic energy terms for the two nuclei You have your electronic potential that's set by the electronic state. And then you solve for the nuclear motion. And here you can kind of simplify the problem because this potential is spherically symmetric. So it's like solving the hydrogen problem. So you chuck that tool once more. You do separation of variables with the y Lm functions, where in this case, the y functions represent the rotation of the molecules. Okay? In hydrogen atom, it would be the rotation of the electrons. Here, it's the rotation of the molecules. And you have your rotational energy that appear for the radial equation. And so if you write down the effective potential or the effective energy that the molecules experience for very low vibrational states at the bottom of these electronic potentials, you can approximate this potential, the electronic potential, as a quadratic potential.
Sir,
Yeah.
how do you know that the wave function of the system,
Mhm.
of the molecular system,
So
it has some electronic wave?
yeah, so the wave function of the molecule, under the Born-Oppenheimer approximation, we assume that it's a product state between the electronic wave function and the nuclear wave function.
Yeah. So what is the? So how are we sure that this is going to happen? Because they can be sort of, maybe they are not separable.
That's a very good question. So that would be the case, the situation when the Born-Oppenheimer approximation breaks down. That would be the case when the electrons do not adiabatically follow the nuclear motion. That would be the case when these electronic potentials, they have avoided crossings, when the energy gap is very small. So those molecules you cannot describe under the Born-Oppenheimer approximation. But for simple diatomics, the BO approximation works very well. You don't have coupled any crossings in these potentials. So approximating the electronic potential at the minimum as some constant, the minimum value of the electronic potential plus a harmonic approximation. You stick this in, then this effective Schrodinger equation for the motion of the nuclei is just also for the partial wave barrier that we consider, or the rotational energy of the molecule. We also make the approximation that at very low vibrational states, we can take the R, the distance between the nucleus, to be the minimum, R0. So that's the rigid rotor approximation. So under these approximations, this Hamiltonian then just looks like a harmonic oscillator, right, for nuclear motion. So you can very simply write down the energy of your molecule as the minimum of your electronic potential, the minimum energy of your electronic potential, which is called the bond energy. You can think of this as the energy contribution from the electronic interaction itself. And then you have your harmonic oscillator energy, which is the vibrational energy of the molecule. And then you have your rotational energy determined by the rotational constant of your molecule times Jj plus 1. J is a quantum number for the rotation. So that's the total energy of a single molecule as compared to atoms. On top of that, you would have fine structure and hyperfine structure. So the thing to remember is that you have, in addition to the electronic energy, vibration and rotation. And now going back to how this limits how we can treat molecules with laser beams is, so the reason why laser cooling works so efficiently for atoms is because you have these cycling transitions where you can cycle off many, many photons in a closed two-level system. And this closedness of the cycling transition is there because of the selection rules imposed by angular momentum. But the tricky thing about molecules is that for vibrational transitions to excited electronic potentials, there's no selection rule for the vibrational transition. So if you shine in an laser beam to a molecule, you excite them, there's no guarantee that this molecule will fall back to the initial state where they can cycle off a photon again. So the number of photons that you can cycle off of a molecule is much less than a typical atom that you can laser cool, which makes laser cooling of molecules extremely challenging. So a typical electronic energy scale is on the order of terahertz, so this is in the photon domain. And then you zoom in, you have vibrational energy on the order of a couple tens of terahertz. And then you zoom in, you have rotational energy on the scale of a few gigahertz. So that's kind of the typical energy scale that we work with in single molecules. So now when you see energy diagram of a molecule like this, you kind of have a better sense, I hope, now. So these different potentials, as a function of the internuclear distance, they asymptote to different electronic states of the atoms themselves. Right? So this, for the case of a pair of a sodium atom and a potassium atom, so NAK molecules, this potential, or these potentials, asymptote to the case where the sodium atom is in the electronic ground state, and the potassium is also in the electronic ground state. Whereas these excited states, this branch corresponds to the potassium, the outermost electron of the potassium being excited. And this branch corresponds to the sodium atom being excited to the p state. And these are all the bone open ion potential that they can actually form through this mechanism. So going back to laser cooling, because of the fact that you don't have selection rules of vibrational transitions, it's very hard to cycle many photons, and it's very hard to laser cool them. But experimental physicists are very brave, aren't we? So there are actually groups that still try to do laser cooling of molecules. And in this case, you need to find very special molecules that have the so-called nearly diagonal Frank-Condon factors. So these are very special molecules where you have a vibrational state in the excited electronic state match very closely to the vibrational wave function of a molecule in the electronic ground state. So the wave function overlap between the ground and the excited molecule, the spatial overlap is very close to 1. So if you excite to that particular electronic vibrational state, with the very high probability, they will come back to the initial vibrational state in the lower electronic state. So you can cycle more photons this way. And state of the art in the direction of laser cooling of molecules can produce about a few hundred molecules at a temperature of a few tens of microkelvin. And if you follow these experiments with molecular tweezer arrays, these molecular moths are actually very good starting points to load them into tweezers. My specialty is in a different approach, the so-called bottom-up approach. And the way in which this works is because as experimental atomic physicists, we know extremely well how to cool atoms to very cold temperatures. So a natural thought could be that why don't we cool the atoms first to nanokelvin temperatures, and then try to figure out a way to assemble them while maintaining this low entropy of the gas. And this bottom-up approach actually works quite well for bialkali molecules. So state-of-the-art experiments in this direction can create up to tens of thousands of molecules at temperatures as low as a couple tens of nanokelvin, so deep into the quantum regime. So that's kind of the experimental approach that we take in my experimental group.
So you first cool down, constituent atoms, and then
So if I take the example of a sodium and a potassium atom, we'll cool a bunch of sodium atoms to about 100 nanokelvin. Same time, in the same experimental run, we'll simultaneously cool potassium atoms to about 100 nanokelvin so that they form a mixture. And then we do pairwise assembly of these atoms. So we bond sodium atoms together with potassium atoms. I'll get to that.
but
few reactions can be exothermals as well. I mean, can release heat.
Oh, you mean the binding energy? Oh, that's a very good point. So, which naturally extends to the next slide. So the way in which we create these molecules, assemble these molecules, so first we have to trap and cool the atoms first. And the second step is that instead of directly forming these tightly bound ground state molecules, we form what's called these Feshbach molecules that are very loosely bound. The binding energy of these intermediate molecular state is on the order of a few tens of kilohertz. So that's a temperature that we can manage. And even that, we do it coherently with photons. These Feshbach molecules, because they're very large, you can really think of them as two atoms put together on a stick. Okay. But from the viewpoint of wanting to make use of electric dipole moments, these very large, fluffy Feshbach molecules are not going to have any significant dipole moment, right? Because the way in which these molecules acquire an electric dipole moment is because the electronic clouds deform through interaction along the molecular axis. And if they're so far away, there's negligible interaction between the electronic clouds. So the third step, which is a key step of these experiments, is that you have to somehow figure out a way to coherently shrink the size of these molecules. And there, the issue of the binding energy comes up. So the binding energy difference between these Feshbach molecules and the tightly bound molecular state, if you convert that into temperature, it's on the order of a few thousand Kelvin. So if you put this much of work into preparing 100 nanokelvin gases, and then you dump like a few thousand Kelvin worth of kinetic energy into your atomic/molecular gas, then these molecules are immediately going to boil out of your trap. So the challenge is you have to figure out a way to do this adiabatically, without heating up. And for that, we use laser beams to coherently drive transitions between the Feshbach molecular state and the ground state. So essentially, a pair of photons will take that binding energy difference away from the molecular gas. Okay? So this way of molecule assembly was first performed in the year of 2008. By the research team at Jee-Woo, where they worked with potassium rubidium ground state molecules. And some detailed story there is that these Carib ground state molecules in their low vibrational ground state, it turns out they have a chemical reaction. So if you have a pair of Carib molecules collide in the ground state, the energy of a K2 molecule plus a rubidium-2 molecule is actually lower. So there's an exothermic exchange reaction that will spontaneously happen. So this is awesome if you want to study quantum chemistry, because this is your favorite chemical reaction that you want to probe. But if you want to do many-body physics with these dipolar molecules, this is a loss mechanism of your dipolar molecules. So since then, there's been a lot of effort into trying to first figure out if there are molecules that do not have this pairwise exchange reaction, hopefully with a very large electric dipole moment. And of the list of the list of molecules that you can create by combining a pair of alkali atoms, personally, my favorite molecule is the sodium-potassium molecule, because as it turns out, these are chemically stable. So this is more energetic for NAK. And they have a very large electric dipole moment of 2.7 dpi, which is about 5 times larger. So in terms of interaction energy, that's 25 times stronger. So this is a molecule that you hope you will be able to cool down to the quantum regime and really have a very strongly dipolar gas of molecules. And because of that, there is a number of different groups working with or trying to work with sodium-potassium molecules, MIT, MPQ, Hanover, CAS, and whatnot. So there's a little bit of competition here. Yeah. No, yeah.
Is that true that I should think of this loosely bound state as some kind of resonance state and then
Yeah, exactly. Yeah, that's.
additively continue to fire tight bound state, so you're just increasing the stability.
Yeah, so we will be using a Feshbach resonance to assemble these molecules.
So in terms of this S-matrix language, you have so for this tightly bound state, you have the solutions very, very close to the real axis and you were shifting the solution with the imaginary axis?
I'm not so sure if I understand your question
Because,
properly.
the resonant points are very close to the real axis of the S matrix. And
The internuclear distance you're saying.
the S matrix.
S matrix. Yeah, yeah.
And then if you shift it to the imaginary axis, it will correspond to the bound states.
Yes, yes.
So this adiabatic continuation is something like...
That's the essential idea of Feshbach association. So that's the essential idea behind how we create these loosely bound molecules. Not the ground state molecules. These are not resonant. Yeah. These are resonant from a scattering resonance perspective. Yeah.
If I remember correctly, in the beginning of the talk, you said we can use.
I'm sorry, can you speak up?
Okay, so in the beginning of the talk,
Yeah.
if I remember correctly, you said we can tune the dipole moment of this
Yeah.
polar molecule.
Yes.
But then from what I see, it's like a tightly bound atom.
So that's if you think in the molecular fixed frame. If you fix your molecular direction to be along, let's say, the x-axis, in that reference frame, these molecules have a permanent electric dipole moment. But in space, these molecules are rotating in random directions. So in laboratory space, the way in which these molecules acquire an electric dipole moment is if you make superpositions of rotational states along a particular axis. So by controlling what kind of superposition state that you make, either using a DC electric field or an AC microwave field, you can control the size of the dipole moment itself. With the microwave, you don't have very continuous control. With DC electric field, you do. I'll get to that on Thursday's lecture.
Just out of curiosity, you mentioned the other process, which is this laser, by using laser.
Yeah.
Just make it to some, some known vibrational state, and then it will come down to the down state.
Yeah.
So, what is the temperature that they have reached?
With laser cooling.
Yeah. So, is it ultra cold or?
No. It's on the order of a couple tenths of microkelvin. They're cold, but cold enough to load into tweezers. And I think they can also do sideband cooling of these molecules with the laser. So that works very well for tweezer traps. So they're not quantum gases. They're mods, magneto-optical traps. Yeah. I think there was another question that I missed, but if not, I'll. Yeah.
So the photons that are carrying these bond energies, can the other molecules like absorb it and like increase its temperature?
Not really, because this is a stimulated process. Yeah. I think if the density of the molecular gas was really, really high, you could have the second order effect where the molecule emitted, I don't know, stimulated in a stimulated fashion or even in a spontaneous fashion, and then that photon will get bounced around. But in these densities, no. Okay. So this is the full list of, I think, I cannot guarantee that it's a complete list, but it's close to being complete, of all of the molecules that have been assembled, bialkali molecules assembled that have been assembled in this fashion up to this point. So our team at POSEC, we work with sodium potassium 40 and sodium potassium 41, which is not on the list because it's a molecule that has not been created yet. We're very close to having them in the ground molecular state. Hopefully by this year we'll have, our name will also be up here. But if you remember yesterday, I showed you this map of all the experimental groups working with cold atoms, and that the number of flags on that flag was quite dense. And you can see that for molecular experiments, for ultra-cold molecules, the list is much shorter. And that's representing kind of the level of challenge that these molecular experiments have to deal with. It's much more experimentally challenging than just working with atoms, this association process. So, do I have time? Yeah, I have 30 minutes. So how do we actually go about assembling these molecules? I'll go through the 3 steps in a little bit more detail. So step 1 was cooling atoms. So, and I've already covered that yesterday using laser cooling and evaporative cooling. We can routinely create mixtures of atoms at very cold temperatures. So that's kind of checked off. I've already shown you an example density image, a time-of-flight image of such a mixture that we can create. Although for molecule association, we don't like to condense our atoms because especially for these dual Bose-Einstein condensates that repel each other, the spatial overlap reduces very strongly once you condense. So we'd rather keep them slightly above the condensation temperature in a thermal gas. That's just one experimental detail. So that's taken care of. And then that brings us to the second step, which is to use these atomic mixtures, ultra-cold mixtures, and figure out a way to create these so-called Feshbach molecules, loosely bound molecules. And here, we're going to use this scattering resonance called the Feshbach resonance, named after Hermann Feshbach, who's a nuclear physicist. And the idea is that in these Born-Oppenheimer potentials, you're going to have vibrational eigenstates, right? You'll have the least bound eigenstate, vibrational state of the ground electronic potential. And the idea is that these molecules also have a magnetic moment. And the magnetic moment of these loosely bound molecules is actually different from the magnetic moment of the two atoms in the scattering state. So that gives us a way in which we can control the energy difference between the scattering state of a pair of atoms and the loosely bound molecular state, just by changing the magnetic field that we apply to our gases. And why is that important is because that allows us to use a scattering resonance to actually adiabatically associate or populate these loosely bound molecular states. Okay, I have 30 minutes. Oh, how many slides? I think I still have quite some slides. So I'll skim through the resonance physics. Presumably you guys already know this. You guys are all theorists, so you can study scattering, the chapter on scattering resonances. But the bottom line is that if you have some potential we can think of having, for instance, a square wave potential. Yeah? You can work out that if the depth of the potential is very shallow, the scattering length of when you have an atom or in the reduced mass frame, if you scatter off, the phase shift is actually towards the negative direction. So you have negative scattering length solutions. But the interesting thing is as you change the depth of your potential, every time that you have a bound state appear on your potential, you have a divergence of your scattering length. Every time that you have a bound state. Yeah. So these are called scattering resonances, and they appear because essentially, in a kind of a heuristic understanding, your pair of atoms are confused whether they're atom pairs or molecules. Now, obviously, when they're confused, the scattering length, you would imagine that their scattering lengths would go crazy. Okay? So that's...
Guaranteed to get one bound state which is of even parity, because the even parity condition is that you are guaranteed to get one bound state for sure. Because there is one, however small the potential is.
I'm thinking about single body scattering in this example in particular, not about two body. If just to simplify the problem, but sure, for a real molecule, you need to be concerned about the parity of the bound state.
I'm just talking about however this V0, however small this V0 may be, the V0, the depth, you will guarantee to get one bound state.
Oh, you're asking me what the depth of the V0 will be for a single bound state?
I think you must get one bound state for sure, because from this asymmetry, you must get one bound state at least.
Oh, I don't think so. If it's very shallow, I don't think you have a bound state.
Okay, maybe.
Yeah, I don't think so. I think you need to have some depth for the pole to appear. But I mean, That's mathematics, so you can check that. But I think that's correct. Yeah. So the physics of Feshbach resonances is now you think about a pair of atoms now scattering off and forming molecules. So you have these electronic ground state potentials. Because you work with bialkylies, you have two electron spins that can pair up, right, in the molecule. So you have the triplet state and the singlet state as your electronic ground state. And simple question that I will ask is which potential will be deeper, the triplet or the singlet? So you combine spin 1/2 and spin 1/2, so you have spin 1 or spin 0. These are the singlet state, the spin state is antisymmetric. So they have to be spatially symmetric, the electronic wave function, which means that they can come close to each other, right? Whereas in the case of the triplet state, they cannot because the spatial wave function is antisymmetric. Yeah? So when the electrons that are in the spin singlet state, the electrons can also have more Coulomb repulsion, but more importantly, they can have very strong attraction with the other nucleus. So that tends to lower the energy. So your triplet state is shallower than your singlet state in the ground state. Okay, so that's just one detail. And the thing is, if you have a pair of atoms that are scattering off, you have your scattering wave function coming in from the large R limit into your potential. And using this notion of scattering resonances, whenever you have a bound state in your electronic potential whose energy matches up with the scattering entrance energy, you can have these scattering resonances occur through a weak hyperfine coupling between the scattering state and the bound state. Okay? So what that experimentally means is that because of the fact that these molecules have a different magnetic moment from the atom pair, just by simply tuning the magnetic field around a particular value, we can have full control over the scattering property of a pair of atoms. So on the repulsive direction where the bound state is real, you have repulsive interaction, so positive scattering length that diverges at the position of the resonance itself. On the other side of the resonance, where your molecular state is not real, it's virtual, it's above the potential threshold, you have negative scattering length, which is attractive. So this scattering resonance, the Feshbach resonance, is the essential tool used in atomic gas experiments that allow you to tune the interaction strength of your atomic gas. That tool, in the molecular experiment, we use to actually populate these molecular states. So the way in which we can do that is just simply by ramping the magnetic field. You prepare your magnetic field and your mixture on the attractive side of your Feshbach resonance, where the molecular state is virtual, and then you just ramp the field smoothly across the resonance. And then these pairs will adiabatically become the molecular bound state. So this is the strategy of magnetoassociation of molecules. Another strategy is to use RF photons. So if you have your scattering resonance in a particular hyperfine state combination, you can initially prepare your mixture in a different hyperfine state. And then you essentially shine in a radio frequency photon and spin flip your atom into the interacting state, where you provide additional energy with the photon that corresponds to the bound state energy. So this is a RF spectroscopy of atoms, of sodium-potassium atoms in the ultra-cold regime. And this peak at resonance corresponds to just spin flipping our atoms. If we add a little bit more energy with the photons, just increasing the frequency of the RF photons to the value that corresponds to the binding energy of these molecules at that particular magnetic field, we can have a second peak that appear corresponding to populating the bound state itself. So in this way, we can frequency selectively populate molecules, associate molecules, and even image them. You can image the shadow of these molecules in cameras. And you can do that for a range of magnetic fields to really map out the bound state energy as a function of the magnetic field. So the slope of this would be the magnetic moment at that field of the Feshbach molecules. So in our experiment, I said we work with sodium and potassium mixtures. As I said, potassium has 3 different isotopes, 2 of which our group works with, the fermionic 40 and the bosonic 41. Right now, our team is able to create both bosonic Na41 K-Feshbach molecules using RF association, and also with the same experiment, fermionic Feshbach molecules. So we can kind of choose. We can really choose, dial and choose the quantum statistics of the molecules that we work with.
So this is a stimulated emission, is it?
Huh?
So you're shining RF that matches this energy gap and make an atomic state of molecular state. Is it?
Yeah.
So this is a kind of stimulated emission?
Yeah. This is a fully Korean process. Yeah. Okay, that gets us to the third step. So we've cooled our atoms, we've populated this loosely bound Feshbach molecular state, and then for our goal of creating dipolar molecules, we want to go down to the ground state of the singlet molecular potential. This is the state where the atoms are tightly bound. They have non-trivial electric dipole moment. And as I said, the binding energy difference for the case of NAK, I think this is on the order of 7,000 Kelvin, I think. So the key is to remove this binding energy difference when going from here to here in an adiabatic fashion. And obviously, you can think about using photons. But there's no single, the first thing that you can think about is driving a single photon transition between these 2 states. But that doesn't work so well because, first of all, these Feshbach molecular wave functions are extremely large in space, whereas the ground state molecules are tightly bound. So these so-called Frank-Condon factors are essentially 0. So you have essentially no wave function overlap that you can drive transitions off of. Secondly, oftentimes these Feshbach molecular states tend to have a strongly triplet character, whereas the ground state is spin singlet. So there's a very strong spin mismatch that also forbids you from doing any kind of single photon transition. So the way in which you have to proceed is to drive a 2-photon transition through this zoo of excited molecular states. And this particular excited molecular state, electronically excited molecular state, needs to satisfy 2 requirements. One, it has to have good wave function overlap with both of these states, so good Frank-Condon factors with both. Second, it has to have a strongly mixed spin character of singlet and triplet, so they can talk to both the triplet state and the singlet state. And this spin mixing in the excited manifold arises because of spin orbit coupling in the molecule, in the individual molecules. So naturally, from an experimental point of view, locating this very unique excited state, understanding your potentials to the point that you know their vibrational wave function and their spin decomposition, and actually experimentally locating the state is going to be a lot of work. It's going to be very challenging, which is a key reason why, one of the key reasons why there are not that many experiments working on assembly of molecules. So if you're given a new mixture, a bialkali mixture, which is a mixture that no one has ever created ground state molecules of, so there's no recipe for you to work off of, then you have to start with doing molecular spectroscopy to understand all of these excited vibrational electronic transitions, right? So that's what actually people do, what I had to do when I was first working with sodium-potassium molecules. So experimentally, what you do is you have a tunable laser, you shine in your laser beam and see if your initial Feshbach molecules are still there after you shine in a laser beam. If they're there, it was a miss. You don't have a bound state at that particular frequency. But as you tune your continuous laser to different frequencies, at some point you will see losses of your molecules, which is a strong signal that you've excited these molecules to electronically excited states. So you're looking for losses of your Feshbach molecules as you do spectroscopy. And you can do that for a range of laser frequency. And you can, at that point, you can map out the losses of your Feshbach molecules and try to figure out the pattern of losses and try to match that with theoretical predictions of the energies of the excited states. And with this understanding, you can try to figure out where good excited states would be in terms of having nearby triplet and singlet states where you can have mixed spin character. Once you have that information of which vibrational state that you want to use as your bridging state, you can do an even more careful spectroscopy to figure out all the hyperfine structure of your molecules, rotational and hyperfine structure. So that's a lot of spectroscopic work that you have to do to create these molecules. And people do that. And this is all actually data that I've taken when I was a student. And then you can undo the perturbation to understand the spectra, including the various molecular couplings, Hamiltonian terms that you have. And then you can really figure out for a given excited vibrational rotational transition what the spin decomposition is of that state and the various quantum numbers associated with the particular hyperfine transition. With that understanding, you can now move into the next phase where you look for the ground state. So if the excited state was not known to begin with, the energy of the ground state relative to the Feshbach molecular state is obviously also not going to be known accurately. Which means that even after finding the suitable gateway to access the ground state, starting from the Feshbach molecular state, you actually have to do two-photon spectroscopy to find this ground state before you can transfer them. So that's another layer of molecular spectroscopy that you have to do. And this spectroscopy is actually quite challenging because the two-photon Rabi coupling that we can afford in these experiments tend to be very small. So the kind of Rabi couplings that we work with in these experiments is on the order of a few kilohertz. Whereas the frequency difference between the two lasers that you are working with to address in a two-photon scheme the ground state, the energy detuning corresponds to a few hundred terahertz. You have two laser beams where you only have about a kilohertz or 10 kilohertz Rabi coupling whose frequency difference is on the order of 100 terahertz. What that means experimentally is that the laser frequency stability of these two lasers that you use has to be controlled within a fraction of 10 kilohertz, while at the same time maintaining 100 terahertz frequency difference. So you have two electric fields, your laser beams, oscillating at a frequency of 300 terahertz with a frequency separation of 100 terahertz, let's say. The phase of this extremely fast oscillation in these experiments have to be stabilized to an accuracy of a kilohertz. That's crazy, right? Yeah, so that's extremely challenging. But still, we can figure out ways to do that. We can lock our lasers to very special hyphenous cavities using a very fast feedback loop. And we can actually do this two-photon spectroscopy and find EIT features, coherent two-photon cancellation of the transition amplitude to locate the ground state. Once you locate the ground state, then you can use the same lasers, the two lasers that you use to do spectroscopy with to actually transition or make the transition go, two-fold transition work. So, and the typical signature of us having created ground state molecules is to see the disappearance of the molecules from our imaging system as we transfer them to the ground state. But then the question is, how can you tell if the molecules have been transferred to the ground state or they have been just lost due to some technical imperfection of your laser system? So the smoking gun proof is to do the reverse transition of the ground state molecules to the Feshbach molecules and see them come back in your imaging system. So you have to do this two-way transfer to confirm that you actually do create these ground state molecules. And typical experiments, in the best experiments, we can typically create about a couple tens of thousands of molecules in this fashion at a temperature regime of like 100 nanokelvin. So this is, so this is one thing that I kind of moved on in the interest of time. But the two-photon transition that we drive, we don't just drive a simple two-photon resonance, but instead we use a technique called STIR-up. It's an acronym for Stimulated Raman Adiabatic Passage. And so this two-photon transition, how it works is that initially you have your molecules in the Feshbach molecular state. So this is your initial state. This is the singlet ground state that we want to reach down to. And this is the excited molecular state that you found doing single photon spectroscopy. Naively thinking, you would think in order to transfer these molecules to the target state, you would either shine these two lasers together, or maybe shine this laser first and then somehow pump this molecule down to the ground state. But the way in which STIR-up works is totally the opposite. Your molecules are initially here, but you turn on a laser that couples the ground state to the intermediate state. And then you gradually reduce the intensity of this laser beam while ramping up the laser beam intensity of this transition, corresponding to this transition. It seems very counterintuitive, right? Because initially you're shining in a laser beam that seemingly doesn't do anything to the molecules. The molecules are initially here. But if you work out the couple 3-level system, what this laser is actually doing is, so if you diagonalize the Hamiltonian of the couple 3-level system with two Rabi couplings in the rotating frame, if you diagonalize it, you have 3 eigenstates, 2 of which are bright states, and 1 of which is a dark state. A bright state is a state that has explicit admixture of the excited molecular state. And the dark state is an eigenstate solution that doesn't have any excited state mixing. So what this laser beam is initially doing is it's preparing the Feshbach molecular state to be in the dark state of this couple 3-level system. What the intensity ramp is doing, it's adiabatically transforming the character of the dark state such that at time t equals 0, it's the Feshbach molecular state, but at time t equals t, it becomes the ground state. So this way, we always maintain the molecules in the dark state of your couple 3-level system, which doesn't have any excited state admixture, which can spontaneously decay out of the system. So this is a very clever trick called STIR-up. And so this figure that you're seeing here is the time of the intensity ramp of the 2 laser beams. So you're doing this counterintuitive intensity ramp and doing the STIR-up transfer to the ground state, and then you're doing the reverse intensity ramp to bring them back. And the y-axis is the number of molecules in your imaging system. This line? Or this line? Oh, this is just, it's a guide to eye. It's a guide to eye. But in principle, you can just do, you can numerically solve the couple 3-level system, putting in the experimentally measured Rabi couplings and simulate this, yeah. So I think I bored you enough. So in the remaining couple minutes, I want to bore you a little bit more because Thursday will be more interesting. So these molecular assembly experiments are really where atomic molecular optical physics meets, right? So you have to have a good sense of atomic physics because you need to cool the atoms, you need to make use of Feshbach resonances, you need to deal with degenerate fermi gases and BECs. But then you need to assemble them. You need to have a reasonable grasp of molecular physics, molecular structures, perturbations, scattering theory, and whatnot. But then you need to have cutting-edge optical techniques using very high finesse cavities and very narrow line width lasers. So it's very technically challenging. There's a reason why there aren't that many ground state molecule experiments in the world. And you can go on, once you create these ground state molecules, you can go on to measure their lifetimes. You can apply a DC electric field and measure the DC Stark shift, which confirms that these molecules do indeed have a very large electric dipole moment. And you can also, using a microwave field, drive rotational states, do rotational spectroscopy using microwaves. One thing that I want to emphasize in terms of controlling rotational states is that controlling rotational states is really key to controlling the electric dipole moments of these molecules, even for many-body applications. So if you want to study exotic many-body physics, even on a theoretical level, using these polar molecules, you need to have a good understanding of how these rotational states work. And the reason, because why that is the case is if you have your molecule in an eigenstate, a particular rotational eigenstate, these molecules don't have any electric dipole moments. These rotational states have definite parity. So if you take the diagonal matrix element of the electric dipole operator for an eigenstate, the dipole moment will be 0 for all of these rotational states. So the way in which you have non-zero electric dipole moments in these molecules is when you mix them. You mix rotational states with opposite parity in a coherent way. And that's the way how you induce electric dipole moments in these molecular gases. So if you start off with your molecules in the ground rotational state, and you shine in a sigma minus polarization microwave field to make a coherent superposition of the ground and the 1 minus 1 rotational state, the eigenfunction of the rotational, the superposition of the rotational wave function will actually be rotating counterclockwise in your frame with respect to the quantization axis, which we normally assume is along the z-axis.
How do you induce rotation states?
So if you have your molecule in a pure rotational eigenstate, so this is corresponding to the rotational quantum number, and this is corresponding to the projection along the z of the rotational angular momentum. So in any of these eigenstates, if you calculate the matrix element of the dipole operator, that's going to be 0 because the dipole moment operator is parity odd as you're taking the diagonal matrix element, right? So in order for you to have a non-zero D, you need to have a superposition of mixed parity states. And once you study angular momentum of these molecules, rotation of these molecules, these excited, so the n equal 1 state has the opposite parity relative to the ground rotational state. The n equal 2 state has the same parity with the ground state, but the opposite parity with the 1 state, and so on. So it's a ladder of switching parity for the rotational manifold. So within this manifold, in order to induce non-zero D, you need to make a superposition of them. The simplest way is just to make a superposition of the ground rotational state with the first rotational state. These are just simple rotor wave functions you can write down. So you can write down these, the eigenfunctions for these quantum numbers, plot them with the energy separation that corresponds to the rotational transition as in the phase factor. You take the norm square, plot it as a function of time, you will see that the squared amplitude of the superposition of the rotational states is actually rotating at the frequency of the energy difference between the ground and the rotational state. So if you do that with the ground state and the sigma minus matching n equal 1 state, these molecules are rotating with respect to the z-axis counterclockwise. If you mix the 0, 0 state with the 1, 0 state, these electric dipole moments are oscillating along the z-axis, along the quantization axis, like this. If you mix the ground state with the sigma plus polarized microwave to the first rotational state, these molecules are rotating in space with respect to the z-axis clockwise. So if you have a gas of molecules, for instance, in a lattice, you shine in a weak magnetic field to define a quantization axis. You shine in sigma plus microwave to create a sigma plus superposition. You're asking how do we control the polarization of the microwave fields? You can do that using what's known as a horn. These are microwave antennas with particular geometries. And by choosing clever phase differences between two frequencies that you shine into a horn antenna, you can control the polarization of the microwave itself to be linear or even to be circular. So this is kind of a control that we can actually do in the experiments. We can actually control the polarization of the microwaves. Does that answer the question? Yeah. Okay. So the way in which you think about electric dipole moments in these molecules is somewhat different from the way in which you think about magnetic dipole moments in atomic gases, which is why I'm trying to emphasize this more again and again. So just before I end, so if you have a gas, a lattice system of molecules and you shine in a sigma plus microwave, you can think of as your molecules pinned in your lattice rotating with respect to the quantization axis. So your dipole-dipole interaction will be averaged over the fast rotation. So that's important. Okay, so these rotational transitions, obviously we can experimentally control using microwave fields. We can drive coherent oscillations. And even do microwave dressing of these rotational states, which is something that I will talk more about on Thursday. And one last thing for the point of quantum computing is that these bialkali molecules, the electronic structure of these molecules look very similar to alkaline earth atoms. What that means is that the hyperfine structure or the ground state structure is such that you only have nuclear spins in the rho vibrational ground state, which are very weakly coupling to any external field fluctuations. So a pair of hyperfine states of these bialkali molecules are fairly well protected against any external field fluctuations. So they make very good storage qubits. And you expect them to have very long coherence times, and which is the case for these bialkali molecules. So this is the first experiment that I performed many years ago, probing the coherence of these nuclear hyperfine states, and indeed seeing that they live for almost a second. And by now, other experimental groups have pushed this number even further to essentially to the lifetime of these molecules in the trap gases. So they're very long-lived. Okay, so I think I've bored you enough today with too much molecular physics. I hope that wasn't too painful, but I promise that Thursday will be much better. Okay, I'll end there.
You talked about this feedback resonant molecular states.
Yeah. Yeah.
Can you why the spin? If I think about two electrons,
Yeah.
Why the spin state has to be triplet?
I don't think it has to be. I guess it doesn't have to be. It's not going to be pure triplet for sure. It's going to be mixed. It's going to be determined by the shape of the potential itself, right? Which threshold state is closer by. I think for bialkalis, I don't know if there's a physical reason behind it, but more often than not.
Tightly bound state I can understand in the following way, because for the tightly bound state has to be singlet.
Tightly bound state will always be singlet. Because your singlet ground state potential is much deeper than the triplet.
Right, and the spatial has to be symmetric, so fairly symmetric.
Yeah.
So that way I can understand the tightly bound one, but how about this?
Well, I mean, the loosely bound states, you have eigenstates in the triplet potential, but also in the singlet potential when they're decoupled. It's a matter of which threshold state is closer to the entrance channel energy.
So suppose if it is singlet in some setup,
Yeah?
then this three
Still, it's not going to work because the wave function overlap is still zero, essentially zero. So you can't derive a single photon transition still. Yeah.
Okay.